possibilities of time travel.
Thank you very much. So at the start, Neil said that he'd start by confusing people, and then we'd have some explanation, and it wouldn't be a talk on theory of relativity if we didn't end also by having a bit of confusion as well. But what I'd like to do is start by trying to explain how some of the important ideas and notions that we know from our everyday life about time, about causality, about past and future, how that works out when you go to a situation where space-time, well, first of all, space is combined with time into space-time, and secondly, that space-time itself is curved and warped, and what can happen there. So, I have a subtitle for this talk about is time travel possible, and I'll say something about that towards the end of this. So, the first thing I want to do is try and say something about the geometry of space-time. When we look at the theory of special relativity, at first sight it seems very different from our everyday experience in that you have time dilation, you have clocks slowing down, and you have length contraction. And that's not something we experience in our everyday lives. However, there is something we do experience in our everyday lives, which is that when you look at something, it looks different when you look at it from here, and if I move around here and look at it, I get a change in perspective. The bit that seemed to be to the left might move to the right, and so on. That change in perspective that you're used to in ordinary three-dimensional geometry in everyday life, it's similar to that, except instead of having a change of perspective in space, we have a change of perspective in space-time. The fact that things get shorter and the clocks go slower are not independent events, they're both part of a change in perspective, which when combined together give you something which is invariant. In the same way as the distance between 2 points doesn't vary because I look at it from a different point of view, although the location of the 2 endpoints might vary, the same thing happens in space-time. So, when you combine space with time, you get something, it's not like the ordinary three-dimensional geometry, it's a bit different and it has some peculiarities, but nevertheless it fits together in a way that is quite natural. Once we're used to this idea of looking at the geometry of space-time, I'll look at black holes, and one of the favourite things that appears in science fiction are wormholes. I'll say something about those. Solutions with closed time-like curves. CTC stands for closed time-like curves. So that means you can start at some point and you can go back into your past. And I'll explain that there are solutions of Einstein's equations with closed time-like curves. Now, Einstein's equations have all kinds of strange things associated with them. They have black holes, they have gravitational waves, they have, as we've talked about, length contraction and time dilation. All these things have been experimentally verified, and it's come through every test with absolute flying colours. So, if the theory does allow solutions with closed time-like curves, then we should take that as a serious possibility. It's not saying they exist, it's saying something that shouldn't just be confined to science fiction because it seems unlikely. It's something that we should investigate scientifically. And indeed, people study the possibility of closed time-like curves of time travel within the theory of general relativity. I'll say something about that. So if you have solutions with closed time-like curves, again, we think to ourselves, it's not likely. We think there are all kinds of paradoxes that might happen if you have closed time-like curves. So what might stop there being closed time-like curves in the universe we actually live in? Talk about something that Stephen Hawking thought about called chronology protection. But there's actually a rival theory which is called the principle of self-consistency, and I'll talk about those two ideas and how they relate to solutions with closed time-like curves. So we've talked about combining space and time. I'd like to give you some ideas about why it is that it's a good idea to combine space with time. And I want to start with what Newton thought about space and time. The Newtonian concept of time was that time was some absolute thing. I think Newton thought time was time as perceived by God or something like that. I'm not quite sure how I thought it. But if we had a notion of now, when I snap my fingers, everyone, whether they're here, some distant planet, agrees on what happened before that. That was things that happened before that event, things that happened after that event. So there's a universal idea of what happened before and what happened afterwards. So there's a universal notion of past and future. I don't think this is a photograph of Euclid, but it's the best I can do. He also had an idea that you measured distance using Euclidean geometry. And I've done what you're never supposed to do in popular talks, but I can't avoid it, is write some equations down. That formula there is telling you how you measure distance, and it's really Pythagoras' theorem. I'll draw the two-dimensional version rather than the three-dimensional version. If you want to measure the distance between those 2 points, and you measure this distance here is the change in the x distance, and this distance is the change in the y distance, then the distance along this side satisfies ds squared equals dx squared plus dy squared. And you can use that not just to measure the distance along a straight line, but if you've got a curve, and we'll come on to this later on, what you do is you divide this curve up into lots of little bits which are sufficiently small that you can apply this formula. You can approximate the curve by a straight line along those little bits. You use that formula on all those little bits of straight line, and you add them up. And in the limit, these little lengths get smaller and smaller. For those that know about these things, you can write that in terms of an integral. So this is how you measure distance, and although it comes from Pythagoras' theorem, which is about measuring sides of triangles, it's actually how you measure the length of anything. Now, for Newton, there was a special class of observers. They were inertial observers. And there's a slight circularity in Newtonian theory about what exactly an inertial observer is, which I won't go into now. But he described them as observers not acted on by any forces. And if you have two observers such that the velocity of one relative to another is constant, then those are both inertial observers. And within Newtonian mechanics, all observers agree on the laws of motion. So Newton's famous law was force is mass times acceleration. And that law is the law that I see if I'm fixed, and that someone who's moving at a constant speed relative to me, they would measure exactly the same law. If I'm not an inertial observer, if I'm an accelerating observer, you don't see that law. So for example, if you're in a car that's accelerating, it feels to you as though there's a force acting on you. It isn't really a force, it feels like a force, it's actually due to the acceleration. That force actually is what's called an inertial force, and Niels talked about in his talk. The force that you feel is proportional to your own mass. It's like gravity that's proportional to your own mass, and that's one of the reasons why Einstein thought acceleration and gravity were locally equivalent. But nevertheless, in Newtonian theory, we're looking at these inertial observers who are moving at a fixed speed relative to one another. Now, one of the laws that people started looking at the end of the 19th century was electromagnetism. And for electromagnetism, it's not true that the laws of physics are the same. If you apply Newtonian theory to electromagnetism, you find that different observers measure a different value for the speed of light. And that's why people had this theory of the ether, that the light was propagating through this ether and observers were either moving in the ether or fixed in the ether. But when people started doing measurements, the famous Michelson-Morley experiments measuring the speed of light, they found that wasn't true. And that was one of the things that led to Einstein's idea that there was a problem reconciling electromagnetism with Newtonian theory. In the same way as today we can't reconcile general relativity with quantum theory, and that's one of the key ways in which people are researching, trying to unify them, Einstein realized there was a problem reconciling electromagnetism and Newtonian mechanics. So Einstein said, well, let's forget about it's just Newtonian mechanics all inertial observers agree on. All inertial observers agree on the laws of physics. And we'll see later on, when he got bolder and went on to the theory of general relativity, he crossed out that word inertial. He just said, all observers agree on the laws of physics. That's the essence, in a way, of general relativity. But for the moment, we'll look at inertial observers. And if all inertial observers agree on the laws of physics, one of the things they can agree on is the speed of light. That seems quite nice, but it has an unexpected consequence. It turns out the notion of time becomes something that depends on the motion of the observer and is no longer a universal concept. One can show this by looking at the equations, but as always, Einstein liked to have thought experiments that explained these. Einstein had trams in his thought experiment because he could see them outside the window of the patent office where he worked in Bern. But I've pinched this one which has trains, so it's a train, not a tram. So how does the thought experiment work? So, here's a train at rest, and what you have here is you have a flash of light is emitted exactly at the centre of the tram, the train, and one bit goes in this direction and one bit goes in this direction, and they arrive there at the same time. And now imagine that the train is in motion, it's moving forward in this direction, and you see, because the train is moving forward, this one, that when it was at rest, they arrived at the same time, the one that's going backwards arrives first, or arrives before that one. Well, so far, that doesn't seem anything that causes you anything to worry about. That's exactly as you would expect things to be. But for an observer on the train, it would be as if you were seeing the train at rest. So for the observer on the train, not this person standing here, but the observer on the train, they would actually arrive at the same time. But for the observer on the platform, the light flash at the back arrives before the flash at the front. So for one observer, the two events are simultaneous, and for the other, they occur in a particular order. And in fact, if you just move it a fraction forward from this centre, you could have the order in which they occur for the two observers is different. And that's completely at odds with what you'd expect from everyday life and the Newtonian concept of time. So here we appear to have things happening before for one observer and after for another. And that immediately makes you worry about causality. How does that fit in with things happening in a causal fashion? Surely that's going to cause us all kinds of problems. In fact, as has been emphasized earlier on, relativity has a speed limit on everything. The speed at which light travels. And that means you can't have something having an instantaneous effect. It takes time from something I do here to have an influence on you. So sound can travel fast, light travels faster, but nothing can travel faster than light. So the time it takes from light to get from me to you is the time anything I do can have an effect on you. So there's a sort of time delay, and we'll see that makes the notion of causality work out. So I'm going to say something is in my past if it could have had an effect on me. So things in the past are things that could have affected me in some way or other. Something's in my future if I could have had an effect on it. So the future is things I'm able to affect, the past are things that can have affected me. Now, one of the things I'm going to use in this talk quite extensively are space-time diagrams. And they're pictures which we use to illustrate how things happen in space and time. In a slightly confusing way, people who work in relativity always choose time going up and space going along. So, if I'm standing at this point here and not moving, I'm going to trace out this line in space-time. That's something that's not moving in space and time is passing. If I'm moving very slowly, to the right, it looks like that. And if I move faster, it moves like that. I'm going to choose units in which the speed of light is 1. So I'm going to measure, let's say, time in seconds and distance in light seconds. If I'm in a theory where the speed of light is some absolute quantity, that's a very natural thing to do. So in units where the speed of light is 1, if I start off at here and I go to the right at the speed of light, that's a line at 45 degrees, and that's a line at 45 degrees. If I start off here, I can't get to these points, because to get to those points, I'd have to go faster than the speed of light at some point. So that's not in my future. It's the bits in here that are. We want to have a three-dimensional understanding of this, so I hope this is understandable. Imagine here, this is a space picture. This isn't a space-time, this is space. So this is the x direction, this is the y direction. A flash of light is emitted, and let's say half a second later, each of the photons is travelling along these lines, these yellow lines, and the photons form a ring in 2 dimensions, or a sphere if if I was working in 3 dimensions. As those things move outwards, in the space-time diagram, so now I've got time going in the up direction, as these move out, they're tracing out these rays, these are the rays of light, and they're all at 45 degrees, that's corresponding to something moving at speed 1. My primitive computing skills, I've had to go as an animation of this here. You can see I'm very primitive, these aren't really very good circles. So this is the space picture, these are the photons moving out and out in a ring. This is the space-time diagram showing them forming a cone. So as I explained on that diagram here, if I start at this point, these points here within the cone are the things that are in my future, because those are the things I can reach from this point in space-time without having to travel faster than the speed of light. These are the things that are in my past. These are things that could have reached me without having to travel faster than the speed of light. If I'd come from out here, I'd have had to go along a line like that, and that line would have had a slope of less than 45 degrees, and that corresponds to going faster than the speed of light. Now, what's really nice is all observers agree on the speed of light. So these cones are not things that depend on a particular observer. These cones are universal objects for all observers. So, in a sense, once you go to a theory where the maximum speed at which anything can travel is the speed of light, it's very natural to have a notion of past and future, which is dependent on these cones. And if these cones were not invariant, you'd have a notion of past and future, which was observer dependent, and that would be even worse. So, actually, Einstein's theory, rather than making things worse, is the only theory you could have where causality works out properly, where you've got a maximum speed of propagation, namely the speed of light. You see, since all observers agree on the speed of light, we recover a universal concept of future and past, not of a future and past of a time, but future and past of a point in space-time. You see, the future, they've got this point, but this point over here, it has its own cone. This is the future of this one, this is the future of this one. Their futures can only interact if there's time for light to get from one to the other. That's the time it takes for light to get from one to the other. So you can't have, in this way of looking at things, an immediate impact. It has to be, you can only have an impact when the futures start intersecting. So as I've said, when you think of space and time, you get a new perspective. Within the theory of special relativity, I haven't time to explain it, you get new physics, you get time dilation and then contraction. But you can think of this as a change of perspective in space-time. Shortly after Einstein came up with the theory of special relativity, Erwin Minkowski came up with the idea of combining space and time into space-time in which you measured distance in space-time using this thing here. And you'll see it's very similar to what I wrote down there. ds squared was dx squared plus dy squared. If I got a z, it would be dz squared. But for once I haven't made a mistake with those minus signs. Very easy to make that kind of mistake in mathematics, get your signs wrong. Those are deliberate. this is how you measure, this ds squared is how you measure times. So if I'm going from this point in space-time to this point in space-time, I measure the distance using a thing that's very much like Pythagoras' theorem. Except this thing here, which I'll call dτ squared, is dt squared minus dx squared. And the fact that this number is smaller than this number tells you that this person, who's a moving person, measures a different time. Now you might think this is just some mathematical nicety, but this equation has been demonstrated in all kinds of ways. We know, for example, from muon particles which enter the atmosphere and they divide into different sorts of subatomic particles with certain half-lives. If it wasn't for this time dilation effect due to the fact that they're moving, we wouldn't measure these remnants from the decay on the Earth. They would have already changed into something else. So we have ample experimental evidence that this is true. And you can see, this isn't some radical new piece of mathematics. It's a bit like saying, well, it wasn't the dx and the dy that mattered, it was the distance between points. Here we're saying it's not the split in terms of space and time that matters, it's the distance between points. Different observers would have that split in terms of space and time differently. Just in the same way as when I look at you, I see you from this position, and I see you from this position, I see a different perspective. It doesn't mean the distance between people, it doesn't mean the geometry changes. So once you get into this way of looking at space and time together, it's not so mysterious, you just think of it as a change of perspective, and we're used to change of perspective within Euclidean geometry. So here's one of the things that's sometimes regarded as a paradox. Time depends upon motion. So first of all, if this wasn't a talk on relativity, but this was just a piece of geometry, and I said, look at those two curves. Are they the same length? Would you tell me they're the same length or not?
Yes, I would.
Well, I'd fail you, of course. Everyone looking at this would say, of course the blue curve is longer than the red curve. What's paradoxical about that? In the same way, when you move through space-time in different ways, you wouldn't expect the length of this curve and the length of this curve to be the same. The only thing is, when I talk about the length, what I really mean is the time measured as you move along these curves. And the other thing that's a bit different is because if we subtract off the space difference rather than add it on, this one, which looks longer, because we're busy subtracting off all this movement in the spatial direction, is the shorter one. So I've said this one is 10 units, whereas this one is 14 units. So that's just a fancy way of measuring the length. That's another fancy way of measuring the length. And they're not the same. This is sometimes called the twins paradox, because here you have one of the twins stays on Earth, the other one gets in a rocket ship, they accelerate off, decelerates, comes to rest, comes back again, and then decelerates. And they've aged by different amounts. Now the reason people think that's a twins paradox is they say, but we're working in relativity. From the point of view of relativity, let's look at the person who's blue. They're going to think to themselves they're the ones that are rest, and from their point of view, it's the red one that's moving. So from the point of view of the blue observer, the red one moves like that, and it should be the other way round. That's how you make it a paradox. It's not a paradox because, remember, at the moment we're still thinking about special relativity. Special relativity relates to inertial observers. From the point of view of this diagram, this red one is at rest. The blue one is accelerating. If you're in a car that's accelerating, you feel that acceleration, you feel the forces. The physics is different. This is a non-inertial observer, actually. And in order to start and end at the same point in space-time, one of the observers has to be non-inertial. It's also why, if you want to go from special relativity to general relativity to say all observers are equivalent, you need to bring in gravity. Because this observer is accelerating, they're feeling these accelerations, and we've just said that gravity and acceleration are in some sense equivalent. And so you need to bring in gravity from looking at this picture if you want to talk about not just special relativity, but general relativity. So, I've said that the past and future is defined by these cones, these null cones. But in fact, that really is the essence of the geometry of Minkowski space. And the thing about the geometry of Minkowski space is it's pretty boring. All the cones just look the same. They don't vary from point to point in space-time. They're the same everywhere. Everywhere in space, everywhere in time. And that's because space-time in Minkowski space is flat. Same way as this describes Euclidean geometry, the ordinary Pythagoras rule, this Minkowski metric is the ordinary generalization of the Pythagoras rule, and it's flat. It's just like Euclidean space, it's flat. We've heard a bit how Einstein came to the general theory of relativity. So, it's a relativistic theory of gravitation, and it has two key ideas. We've already heard about the principle of equivalence. The principle of equivalence tells me that you can't tell the difference locally between acceleration and gravity. But there is a way in which you can tell the difference between acceleration and gravity, because if I drop two particles, you might think they go downwards, but they actually go towards the centre of the Earth. They actually very slightly get closer and closer together. They don't form in parallel lines, they actually get closer and closer together. Whereas, if they're just in space, weightlessness, and I accelerate, they just stay in parallel lines. So you can detect the difference between acceleration and gravity, not by the effect on an individual particle, but actually on the relative motion of the particles. And Einstein wrote down his equations. I've moved my cosmological terms onto the right-hand side and incorporated them in T. So that's just not really a change of equation, it's just a change of how I define my things. And on the left-hand side we have the curvature of space-time, and on the right-hand side we have the energy momentum of matter. And you've already heard the quote from John Archibald Wheeler. We'd like to see a picture of him, and he's got a t-shirt on saying Black Hole Valley, I think it says. Okay. When Einstein came up with his equations, if you write them out in full, we write them in two symbols, because mathematicians, as Neil said earlier, are very lazy, and we find easy ways of writing down complicated equations. Schwarzschild was able to write down a solution of Einstein's equations. And for those of you that are interested in equations, that is the solution. It's not that complicated looking. Even if you don't understand what it means, it's not that complicated looking. But I'd like to try and explain what it means geometrically. And the point about black holes is that they form when the gravitational field is so strong that you can't have light escaping. So what happens is the null cones get sort of, as we move in, so this is as you go closer and closer to the centre of the star as you move in that direction. This is time still going up here. The null cones, the light cones, tip over because the ones that the light that's going out is sort of dragged in a bit by the star. The ones going in go in even more. Until you reach a point here where even the ones that you think are going out are just staying where they are. And when you go beyond that, even the outward going ones are going in. You see what I mean? Okay. The gravity is pulling the photons in so that here, if I start here, the photon can either go in this direction, which is increasing radius, or this direction, which is in towards the star. You can do the same here, but by the time they reach this point, a photon emitted here can either go in towards the star or up there, just stay where it is. Whereas these photons, they can either go in towards the star rapidly or in towards the star a bit less rapidly. The gravitational field is so strong it's dragging the photons in to smaller and smaller radius. And you can see that geometrically in these pictures. Okay? So I'm going to have lots of these pictures. It's important you understand it. These are telling you how the photons can move. If you know how the photons move, that tells you about past and future. Because remember, my future is in this bit. I can't go out that way because that would be going faster than the speed of light. That's not allowed. So my future is everything to there. My future here is everything there. So what I've done is I've drawn another picture here. So these are the cones again. And this is showing what happens. This is a world line. I'm going along. But once I reach this point, inside this line, inside r equals 2m, I pass the point of no return. My future says I have to end up at r equals 0. That's what happens. That's why you get gravitational singularities associated with black holes. Once you've crossed this event horizon inside the black hole, you're sucked in to r equals 0. There's nothing you can do about it. Here's a three-dimensional picture. The same thing. One way of understanding the curvature of space and time is this rubber sheet geometry. You may have seen it outside. We've seen it a bit more today. It doesn't completely tell you about the curvature of space and time. What you're doing here is you're describing a two-dimensional surface curved in 3 dimensions, and that's trying to give you an impression of what it's like for the 3 dimensions to be curved in 4, and that's not an easy thing to draw. So this is just an impression, really. If you do that for a black hole, you get this very curved picture like this. Now, there's nothing in Einstein's theory of general relativity that says time has to go in one direction rather than another. If I replace formally in equations, I can replace t by minus t. So just from the mathematical point of view, I can just replace t by minus t, and you can create a thing that looks like a white hole. That's a time reverse of a black hole. We don't think these exist in nature, but mathematically you can create one, believe in one. And then what you can do is you can actually glue a white hole to a black hole like that. These are things that people in science fiction like a lot. If you've seen Interstellar, where he bends over a piece of paper and puts a pencil through it. Well, it's a bit more complicated than that. You've got to do a bit of engineering with a white hole and a black hole, and you have to glue them together along here, and you need some negative energy to stop this thing collapsing in on itself, which it will do very quickly. So these are very hard to build in nature, but geometrically you can imagine what happens to them. I want to say a bit now about solutions of Einstein's equations with closed time-like curves. The idea is not that you'll be able to travel backwards in time, literally, by allowing time to go backwards. It's a more sophisticated notion of that. The sophisticated notion that you have is that you're going to change the geometry of space-time so that even though locally you're travelling into the future, because the light cones are kind of have this complicated arrangement, locally you're travelling into the future, into my future, into my future, into my future, into my future. Oh, I've arrived in my past. Okay? That's the idea. And thing is, we can write down solutions of Einstein's equations where you can do that. So what I want to do is first of all show you that you can have solutions of Einstein's equations with this property. And then I'll say something about, well, what goes wrong with physics if you do. So you can ask two questions. You can try and understand classical physics, and you can try and understand quantum physics. Now, the interesting thing is that solutions with closed time-like curves date from quite a long time ago. The first one I'm going to give you is one which involves a rotating cylinder. That dates from 1937. And the second one is the Gödel universe. That was a solution of Einstein's equations. It was invented by Kurt Gödel, who was actually a logician, and he worked at the Institute of Advanced Studies in Princeton and learned relativity by talking to Einstein, who was also at the Institute of Advanced Studies. And he thought he'd give Einstein a birthday present, and the birthday present he gave him was a cosmological solution, which is called the Gödel universe, and it has closed time-like curves in it. And Einstein was very, very upset by this birthday present. And then there's some other solutions which have closed time-like curves. In fact, the Kerr solution, which is a rotating black hole solution, can have closed time-like curves if you give it more angular momentum than it should have. It also has naked singularities. So, the Van Stockholm solution is time travel made possible by the rapid rotation of an infinite cylinder. So you'll already guess that maybe this isn't too physical, because it's not so easy to go down the shops and buy infinite cylinders. And what's more, you need to make the infinite cylinder very dense, such that it would probably form a black hole, were it not for the fact that it's going to rotate very fast, so the centrifugal forces roughly balance the gravitational forces. But nevertheless, we can write down this solution in closed form. It's a thing called the Weil-Papapetro type metric. I'll not give you what it is. But here's the space-time diagram. Force, or field. And that is making the null cones tip over like that. But the cylinder is rotating. And one of the effects that you get in general relativity, it doesn't happen in Newtonian theory, and what's more, it's an effect that has been measured, so we know it's a real effect, is if the space-time is sort of whirling round, it has a dragging effect on the inertial frames. It actually, there's a coupling between the rotation of space-time and the gravitational field you feel. And that, you can see, means that the null cones don't just tip over in the direction of the cylinder, but they tip over an additional amount in the direction of the rotation. And I hope you can see this. So they've tipped over, here you can see that's a good picture, they've tipped over in the direction of the rotation, but they've also tipped towards the cone. And when you get in close like that, they've tipped over right like that. So if I start here, I can go down and I can sort of corkscrew my way down, backwards in time, although I think I'm going forwards in time. And actually my watch is going forwards in time, nothing's happening. I go there, oh, I'm in my past. Okay. This is Gödel's present for Einstein. This is a space-time diagram of the Gödel universe. So here we are. I'm starting off here. It works a bit differently in this one. I start off here, you go outside, the rotation gets kind of bigger as you go out in the Gödel universe. You go round here, you go round here, you go round here, you go round here. Oh, I'm back in my past. So, there are solutions of Einstein's equations where it is possible to travel from your present into your past. Now, that does not mean the universe is like that. You will have observed that the first example I gave you involved something a bit unphysical, an infinite cylinder. The second one is a cosmological one. That's to say, the universe has to be created like that. This is not the sort of universe that's created in anything like the Big Bang. So Stephen Hawking asked a different question. He said, in our existing universe, could we manipulate, in principle, the geometry of that universe by getting masses to move, changing? We know that how matter moves affects the geometry, so can we just, in principle at least, have matter moving in such a way that we can distort the geometry of space-time to build ourselves a time machine? That's the question he asked. I'll leave that. I'll come back to those pictures in a bit. So, what he actually showed was that if you start off from a nice, regular piece of space-time and you try and build a time machine, that's to say, form a closed time-like curve in a finite region, you can't do it without violating what's called the averaged weak energy condition. That's to say, the local energy density, on average, cannot be negative. It's important that we have here the averaged energy condition because, as Marco explained in his earlier talk, it's possible at the quantum level to have some negative energies. They kind of come into existence and disappear in a short period of time. But if you average it, that stops those quantum effects counting. So this is a theorem that he proved. He actually proved it using many of the ideas that went into the proof of the so-called singularity theorems. The singularity theorems are the theorems that transformed our belief in black holes to a certain extent because they showed that it wasn't just the Schwarzschild solution, spherically symmetric collapse, that leads to a black hole, but anything close to spherically symmetric collapse will produce a black hole. So it's nothing to do with the special symmetry of the Schwarzschild solution that gives you a black hole. It's anything close to that that also does it. And using the mathematical methods that Roger Penrose and Stephen Hawking developed in proving the singularity theorems, he proved this result here. But there's another thing that can happen. Another reason why you might not believe in time travel. So what I've got here is I've got a region of space-time where you have time travel and a region where you don't. So you're imagining that we've managed to create our time machines from here onwards. Okay, we've built our time machine. And then you can look at what happens to the future of that and what happens to the past of that, and that gives you a thing, this is called the chronology horizon. This divides the region between where you can have time travel and where you can't. And on this chronology horizon, that's just where time travel is barely possible. So that means, just on this region here, a photon which is the thing that can most easily travel backwards in time, in a certain sense, can go back in a closed time-like curve. So you can have a photon moving along a closed time-like curve. And what you find is, as this photon goes every time round here, it gets more and more blue-shifted. Blue-shifted means the energy in that photon gets larger and larger. And the energy just builds up and builds up until it becomes infinite. And then causes the energy to diverge on the horizon, and that makes this horizon unstable, and you actually get a black hole swallowing up the time machine. So if you try and build a time machine according to this Hawking way of looking at things, it gets swallowed up by a black hole, and that's why we don't have time machines in the universe we're in. If there were any, they'd be inside black holes and swallowed up. Now let's say at the end that there are actually some loopholes in the Hawking result. The Hawking result isn't quite as definite as you would really like it to be. And there's some counterexamples that get around the Hawking result. So there's an alternative thing which is called the principle of self-consistency. Which is to say that if you have a space-time with these closed time-like curves, actually what can happen in the future is only what can happen in the future in a way that's self-consistent with the closed time-like curve. So the physics doesn't allow you to have the paradoxical situations. Now, the sorts of things that you think about in terms of paradoxes involving time machines, you go into the past and you kill your grandmother and therefore how did you come to be born, that kind of thing, don't involve physical fields. And they're not easily looked at in terms of mathematics. Indeed, the whole notion of free will isn't something you can solve using mathematics. So those kinds of paradoxes aren't the sorts of ones one can look at. It's best to look at paradoxes that arise in terms of physical fields on this space-time background. And the way in which you look at that is a thing called the Cauchy problem. It's the way in which you understand how a field, how light or electromagnetism evolves in time, given how it starts off initially. And you find that although you might think you could get paradoxes, you don't. It evolves in such a way that it's influenced by the closed time-like curve, and everything turns out to be self-consistent. Absolutely extraordinary. So that actually is an alternative. Maybe you do have time machines, but everything works in such a way that it's all self-consistent. Actually, I believe my own personal view is there aren't time machines at the macroscopic level that can apply to people, but maybe something like this does happen quantum mechanically. So there's a nice little paradox with a billiard ball entering a wormhole, returns at an earlier time to the other end of the wormhole. It can then hit the original billiard ball and deflect the ball so it never entered the wormhole. So that's a kind of physical example of the random paradox. But actually, what you find is there's a set of what's called self-consistent initial data. What happens, actually, is the returning billiard ball doesn't knock it so it doesn't enter the wormhole, it knocks it exactly to make it go into the wormhole. And if it hadn't been for itself coming back, it wouldn't have gone into the wormhole. And you can really convert that example into a solid piece of mathematics involving physical fields propagating on closed space, curved space-time. So the question is time travel in principle possible with paradoxes prevented by this principle of self-consistency? Or maybe it's completely forbidden by the work that Stephen Hawking has done in chronology protection and stronger versions of that which have since been done. I used to think it was completely impossible for there to be time travel, but actually in 2005, Amos Ory constructed a new solution of Einstein's equations, which does have closed time-lap curves, and satisfies, it has a sort of, gets through a loophole in the Stephen Hawking result. And so maybe time travel is possible after all, and if it is, I've got more than 10 minutes left on my talk, but I think you've probably had enough relativity for today. So thank you very much.
So we do have a few minutes left for questions.
For all our speakers today, yes, I can't answer them, Niels will answer them.
So James,
Oh, you'll ask them instead.
if time travel now is possible, how come there's not time travel from the future here, having done your homework and telling you what's going on? Maybe there is one in you.
It's all self-consistent, you see. Someone back in the room, but they're not letting on the answer.
No.
I told you I had a dream last night where I gave this talk. And someone, as I was coming into the room, I met the person who used to be head of department at the university I used to be at, and he said, "You were supposed to give this talk 35 years ago." Right?
No questions?
No questions? I've bamboozled them to... Oh, we do.
Well, just a question, maybe more related to the past than the last couple of years, but about the gravity. Is it a force? I mean, I think that was
okay.
Slightly at the end of the last one. There was a little bit was creeping out about. Is it?
So. Within the theory of general relativity, properly speaking, gravity is not a force. It's simply a reflection of the fact that space and time is not flat, it's curved. But it's a bit like when I say to you, if you're in a car that's accelerating, you think you feel a force. And I say, oh, no, that's not a force. That's just acceleration. Or if if you're on one of these fairground things that goes round and round really fast, and it feels as though you're lying on your back, the wall of death type things. And I say to you, oh, no, that's not a force. That's just centripetal acceleration. Well, to you, it feels like a force, right? To me, gravity feels like a force. So the fact that in my mathematical description I'm not describing it as a force, but I'm describing it in terms of the curvature of space and time, that's just how we do things in a sense mathematically. So questions like, is such and such a force, I don't think are completely clear questions, because what you count as a force is to do with how you measure forces. Physicists like to have operational definitions of things. And within Einstein's theory of relativity, actually, you measure space and time in such a way that the speed of light is guaranteed to be invariant for all observers, because that's how you've operationally set up the way in which you measure time and distance. So, the way in which you measure and appreciate the world is not independent of the theory. Now, I said to someone earlier on today, I wasn't very keen on the philosophy of science. I was more keen on the sociology of science. But I think these kind of questions do stray into the area of what you mean by a force, and it's not quite so straightforward to answer. There are most of the ways in which within relativity or within quantum gravity you think about gravity, you don't think of it mathematically as a force in the same way as you think of other forces as a force. So in that sense it's not a force. But in terms of how it feels to you as an individual, it feels just like a force to you.
But people say, if you get say there are four forces, there's an electromagnetic.
Yes.
And strong and weak, and gravity a force? That's the, I mean, I guess that's the interesting one. On one hand,
Well, I think there are people who believe in ground unified theories that think it's a force just like those other forces. And there are other people that think it's a very different sort of force.
yeah.
So until we have the complete theory of quantum gravity, I wouldn't say there was an answer to that question.
Okay. You're saying there is still...
From the perspective of general relativity, I would not describe gravity as a force, but there are other perspectives from which it does seem to be like a force. And once you start talking about gravitons and things like that, then you are using the language of quantum physics and forces in quantum physics and so on. So that, we don't have a complete theory, and that's why we have this different ways of talking about it in different settings.
I comment on that. I think it's true that the whole of modern physics has dispensed with the notion of force, and you only use it in a rather colloquial, loose way. But when it comes to equations, you put in things like potential energy,
Yes.
and then you from that derive a thing that you can, if you wish, call force. But
Exactly.
it's not a term that's used in anything other than a sort of colloquial, loose fashion. I'm sorry.
So there's a lot of colloquialism around. Yes.
I think the point about the notion of force requires a notion of how you measure the force and a notion of what you're measuring it relative to. And those are the two bits of gauge theory of field theory and gauge theory of general relativity, if you want to be technical about it.
Can you have gravity between photons?
Yes, I would say yes. Marco is nodding. You see, we're into quantum, I have to look to the expert. But I would say yes.
But photons carry energy, and anything that has energy, actually, by the famous formula of Einstein, E equals mc squared.
So you can look at what's called the Einstein, I was going to say you can look at what's called the Einstein-Maxwell equations, which is Einstein's equations coupled to electromagnetism, in which the right-hand side of Einstein's equations, this is the energy momentum tensor of the electromagnetic field. And so you get Einstein's equations plus Maxwell's equations, and they're coupled by the fact that the energy momentum of the electromagnetic field is a source for the gravitational field.
And is that the sort of thing, has that been experimented in other experiments that have shown that effect or verified that?
Not so easily, because astrophysically you don't get large charged stars on the whole, but you get magnetars. So I don't know.
No,
Does that come into it?
no.
I didn't think
I
so.
think the problem you have with this kind of discussion is that if you want to look at the gravitational interaction between, say, two photons, the problem is you can't screen the gravity from everything else.
Yes.
There's one big problem, difference between electromagnetism and gravity is in electromagnetism you always screen charges by putting up a screen of the opposite charge, right? In gravity there's only one charge, everything falls down. There's nothing that says, oh here's another kind that makes everything fall up, and I put a little bit of the up with the down and then nothing happens. Right? We can't do that, and therefore because you can't screen everything else, to set up some kind of experiment where you measure the gravity between two light particles is just almost inconceivable. Because your measuring device is probably going to be heavier than these guys, and so that's going to attract them probably more than what they say.
But Niels, there was that guy called Chris Clarkson who looked at the effect of gravitational fields on electromagnetic signals, didn't he?
It's a completely different story. It's just talking about the coupling you have on the board that says that this. If you
It's
change,
the background,
yeah,
it's not.
yeah,
Okay.
yeah.
So it's it's looking at the effect of the gravitational background on the propagation of the fields, not the gravity. Right.
Okay, I think that is it for today. I hope you've enjoyed today and that you have a good rest of the weekend. In the meantime, I can ask you to thank the speakers you've got here.